In our last video, we considered the creation of the transfer function when given a physical description of some situation or some process unit. So from our understanding of a physical system, we were able to develop the time rules, i.e. a differential equation in time, and we translated that into the Laplace domain using the usual Laplace transformation. We found generally that we had some function in the S domain, so we had some output given as some polynomial function in S, and we could separate that into inputs and into the process, and we could create a transfer function which was the output divided by that input function. So writing it like this allows us to disaggregate the process from the inputs to the process. That is, we want to be able to separate out the action that we are going to take in trying to control that process. And the reason we'll do that is because we are going to try different control strategies. So we want to separate the input's influence from the process influence. And so that's why we create these transfer functions. We take our output, we divide out the influence of the input on the output, and we end up with a transfer function that gives us some insight into how the process behaves. So we can develop our understanding of the process behavior, and then we can try different control strategies. So once we have this, we can then consider different control strategies, and that means we can just multiply by a U of S in considering the responses by that system to some control action. And in this video, we will look at specifically how we can do that. So I'm not just speaking in the abstract here and expecting that we'll be able to do this just from this comment. So this whole video is about the process of doing that. Right? And of course, quite often we'll be applying that we are working in terms of deviations and so on. Now anyway, our control action is typically represented as a U of t. We know in the time domain our output is a lowercase y of t, and so the control action is U of t. And so depending on the time function for u, we can Laplace transform that same function, U of t. We can Laplace transform U of t, and we get a capital U of S. So here, if we apply a step input, you can see there was no control action exerted before 0, and then after time 0, we step up our input to m. So this is a time function. And if we transform that using the step function, the Laplace transformation gives us that that's simply m over s. And in fact, we did identically this example in our Laplace transformation exercises. So we've already seen this transformation. We've done this integration. Please refer back to the second lecture in the series to find the derivation for this. In a similar way, we had considered also the ramp input. So if we have no control action exerted before 0, and then after 0 and at 0, we increase the control action by a fixed gradient. So it's 0, and then the control action ramps up after 0. Then we can represent that by this time function, and then we can Laplace transform. So again, go back to lecture 2 and you'll see that the Laplace transform for this function is simply this one. And so most of these are in the same vein, right? The rectangular pulse we had also looked at, and we had shown that the Laplace transformation of that looks like this. And the sine wave input, we had also shown that was the Laplace transform. We had said the Laplace transform for the Dirac delta function is given by this. It's a 1, and so on. So you can go back and revise these things. So generally speaking, we are applying some time function for our inputs to the system, our manipulated variable, the stream or the action that we are taking. We are exerting some action over time, and we can find the S domain analog to that function. So that's our U function. And again, we are doing this because we know that we can compose for ourselves the transfer function. So in lecture 3, we looked at how we can compose transfer functions. And now we are saying we are unpacking this part of it. So we are considering different control inputs, so sine waves and so on. We can just multiply this transfer function by this input S domain function, and that will give us the response of the system. So let's look at some examples in that. So first off, let's consider our first order systems. And if we go back to the notes, and in fact, let's look at what we did in lecture 2. So in lecture 2, we had developed this big table of transformations. And so you've got the time domain function here, and then the Laplace domain function here. And let's look at a first order system. So a first order system, remember first order will give us a time domain solution like this, right? E to the minus t times something. So that's a typical first order solution, and even if there are several contributors to that first order action, it typically lands up as a sum of these exponential functions. And those would then be contributions from various 1 over tau s plus 1 type terms. So in the Laplace domain, first order system appears in this way. In the time domain, it appears in this way. So anyway, we've got a first order system, and we will look just now at a proper explanation of a physical process and how that arises exactly and so on. But anyway, for now, let's accept this is the first order system. It's typified in this way. So for our process, this is the transfer function for our Laplace domain in first order. And we want to consider different control actions exerted now. So we've just said our output is actually our process transfer function multiplied with the control action itself. And so if we are applying a step input, then that's m over s, as we just mentioned, right? So if we do that multiplication, m over s times k tau s plus 1, then this is the Laplace domain version of our output. And to get the time domain version of that, we can just do a table lookup. And we can see tau s plus 1, and that times s, and there's some constants on top there. So if we go back to our table here, right, we've got s times tau s plus 1, and then we have a 1 minus e to the minus t over tau. And in our transfer function, we actually have k times m. So you can imagine there's a k times m on the outside. And that's the same as what we have here. So we can say for our first order system, if we apply a step input, then we will get this kind of response. And if you think about that a little bit, if you imagine a first order system, let's say, for example, it's a pressure release from some vessel. You can imagine the pressure dropping in the vessel, and let's say we step increase the applied pressure at the inside the vessel. Then that will cause a rise in the exit flow rate from that vessel. So if you imagine, this is showing us the output, right? This is a graph. This is a graph of this output, and this is in response to some applied step increase. So if, for example, you cranked up the flow rate into the system, then that will cause, let's say that was the exit flow rate, then that will cause the exit flow rate to rise, and then it will settle down to some new value. So you've step increased your input, and you didn't make any change after that. You've stepped it up to a new value, and you maintain that new value. So then the system will respond by increasing in its output, and then it will settle down to the new value. So it will take some time to settle down to the new value because there'll be some lag in the system. It will take some time for the system to respond, but it will respond and it will settle down to the new value because all we've done is step increase that input. So we stepped it up and then we didn't change the value. So if you imagine here that we increased suddenly, let's say it was a temperature in a steam generating vessel. So we step increase the temperature to some new value. And so the output of steam increases slowly, and then it reaches a new value and it stays at that new value afterwards. And of course, if we went ahead and changed the temperature again, we increased it again, then of course that would respond by increasing slowly again to the new value. So we expect to see this kind of response. And in fact, this is quite, it's quite common, or I'm not sure how to say it. It's almost a canon, right? It's quite well documented, the response of first order systems, right? The exponential decays, and there are special names, half-lives and things like that. So this is very well studied. It's tabulated, and in fact, this representation is really nice because it's written in terms of a dimensionless time. You've got t over tau here. So this is e to the dimensionless, to the minus dimensionless parameter here. Here, of course, you divide the output by km. So that's shown here. You divide by km, giving you a nice dimensionless form. And so we can write the time in terms of multiples of the time constant tau. And so then whatever first order process you have, you can multiply by your time constant and by your degree of increase or degree of step, and by your process's constant, and so you can translate these intrinsic values into your exact values for your process. So this is a nice intrinsic way of representing this whole thing. Anyway, that's I digress there. This is the response to your first order process, which is exposed to a step input. Right, now let's take that same process, and instead of a step, we are applying the ramp input. So remember, in the ramp we have that your input is constant, and then you start increasing it after that. So instead of it being constant and then you step it up to a new value, now you are 0, and then you increase it linearly with time. And then the Laplace version of that increase in time looks like that. And so this time we have to multiply by a over s squared. And there isn't a direct transformation of this, or inverse transformation of this s function back into the time domain. However, we recognize that we could seek a form that does have a representation on the known table. So we can say, well, this is my transfer function, but we anticipate that there may exist an alternate form for this. So we can say, well, maybe there exists alpha over 1 over tau s plus 1 plus alpha 2 over s plus alpha 3 over s squared. And so if you propose this alternate way of creating this function, then it's just a matter of finding the alpha values which make this true. And you can find that by multiplying both sides of this equation by s squared tau s plus 1. Okay, let's just do it here quickly. So I'm just going to copy this. And if we multiply this by s squared plus 1, then of course on the left-hand side we'll have just a times k. And then here we will multiply out the tau s plus 1, leaving us with alpha 1 s squared. And then here this is going to have an extra tau s plus 1 times s. So it's going to be alpha 2 times that. So alpha 2 times that times s. And that's there. And then alpha 3 is that. Not an extra s. Oops. Okay, so that's just a bit of algebra. We've just multiplied the left and right by s squared tau s plus 1. And now we can just consider some special values to obtain alpha 1. So we can imagine to get alpha 1, if we just apply s equals minus 1 over tau, right? So s equals minus 1 over tau. Let's just do it here. So we'll have the AK on the left-hand side still. S doesn't appear there, so that stays as is. So we'll have here alpha sub 1, and then it's minus 1 over tau. So this is going to be tau squared plus, and then if we apply in here minus 1 over tau, then this tau times that is going to be minus 1. And so minus 1 plus 1, that's a 0. So both these will be 0 for the same reason. So these all vanish. And so we can say quite easily alpha 1 is then, and I'm just going to write it here, alpha 1 is tau squared times AK. Right, alpha 1 is that. So we've already got alpha 1. Then for let's say alpha 3, if you take alpha 3 here, if you take s equals 0, then quite simply you'll get alpha 3 equals, so applying 0, you can see s equals 0 here will make this thing 0, and s 0 here makes that 0, leaving us with simply tau. So tau s disappears here, s equals 0, so that leaves us with just the 1. And so this is AK. So alpha equals AK. Alpha 3 equals AK. And then for alpha 2, let's see, what could we apply there? Well, you could apply virtually any value here. You could use s equals 1. 1 over tau is a good choice. And you would be able to evaluate all these. You already have alpha 1 and alpha 3. Those were easy to get. And so by applying just one other value like s equals 1 over tau, you can by difference work out what your alpha 2 is going to be. And then you have all the alphas defined, and so you have now found the alternate form to this equation. And once more, we are free to propose such a thing, right? We don't, in principle, have from our algebra that we can expand it like this, but we can propose, well, what must these alphas be such that this is true? And by cleverly choosing these specific denominators, it turns out that such an expression does exist. Of course, if you go and arbitrarily propose some function here, then it's much harder to find that form. It's much harder to represent if you don't choose terms that have the capacity to exactly mimic this form. So this is an exact expression, even though we just chose to represent it like that. So that's known as Heaviside partial fraction expansion. So anyway, we have now expanded this form for which we don't have a known inverse transformation. We've translated it into this form, and we do, if we look at each of these, we can convert each of these, we can invert each of these, right? So it looks like this. That's the Laplace transform in this form. And if we look at this, we regard Ka tau squared, those are all constants, and then you've got 1 over tau s plus 1. So that's the first order Laplace representation. And so that's x minus t over tau, and so you can see that here. And then you've got the minus 1 over s, so that's 1. And again, we've got the Ka tau here. And then you've got the 1 over s squared, which is a t. So it's Ka t. So this is the time domain version of that expression. And again, this is for the same first order process, just with a ramp input applied. So we've applied a ramp input, and this is what we get. This is what we get in the time domain. And if you look at this, we can see that as time increases, this goes towards zero, right? As t goes off to infinity, this whole thing becomes a zero, leaving us with simply kat minus 1 times ka tau. And so the limit as t goes to infinity for y of t is kat minus tau. And if you think about this, then this is telling us basically that we are going to get a straight line in t, right? We are going to get some line that's increasing as time increases. And it's somewhat offset here, and that's because of that exponential contribution. And here's a graph for that. So this is the input that we've applied. So our input, remember, was 0, and then it was increasing at a fixed rate after that. And then here's the solution if we graph it out. So you can see it started from that 0. There was this curve here as the exponential has some significance. And then as t gets to around 2.5, the significance is very low, and we are basically looking at AT. So this is the response, this is the system responding, this is the input, and here it's labeled. You can see the input and the output. And so we get the output lagging the input by tau, right? So it takes about tau before the system starts showing the same rate of increase as the input, but that is what happens after about 2.5 time units or time constants have passed. So that's the response to a ramp input. Now let's look at a third version of that. We want to apply our sine wave input. And going back to our table, for a sine wave, right, this is in the time domain. For the sine wave, it's omega over s squared plus omega squared. So that's what we have here. And we are also applying some amplitude. So this was a pure sine wave, omega over s squared plus omega squared. If we have an amplitude to that, then we have to add that amplitude in there as well. So our input has some amplitude, which we are denoting by a, and so in our transfer function, it's a omega over s squared plus omega squared. So that's our input, and then again our output is going to be the input multiplied with the process itself. So there's the input, and then there's the process, the first order process. So if you, again, we seek some alternate representation because we don't have a Laplace transform inverse for this product here in the denominator. And instead we seek a form like this. And by the way, this one is a little harder to come up with, and it took me about a couple of hours to figure out that this was the transformation that we were applying. And that's because we want certain properties. We want a form that's not going to have imaginary numbers in it and so on, because we seek nice compact expressions, and we just don't want to show imaginary numbers in our solutions here. So this is the proposed form, which is equivalent, or I should say, for which we can find an equivalence with this form. So this form, we know how to arrive at this. We know just our first order multiplied by our input, that gives us this. And now we want to expand this to a form that we can invert, right? There do exist nice inversions of these. And we have to propose, in this case, this version of that equation. So our tendency might be to say, well, take a1 over s squared plus omega squared plus a2 over 1 plus tau s. And I do invite you to pause this video and try and do it that way. And you'll find that it becomes quite difficult to make this, to find an equivalent, to find A1 and A2 that make that true in a compact way. It's hard to do that without getting imaginary numbers in A1 and A2. But instead, if you use this form, you can show quite nicely that it simplifies to the form below. And I think here I am showing that I'm showing the steps involved here. So if we adopt this form, if you multiply out by s squared plus omega squared times 1 plus tau s, of course the left hand side becomes ka omega, and then the right hand side becomes a1 multiplied by 1 plus tau s, and a2 times s squared plus omega squared. And you can sort of see here why it was chosen in this way, why we chose 1 minus tau s here in this numerator. And that's because when we multiply these out, even if s is imaginary, then that's going to cancel here, right? Well, anyway, let's do it. First, let's get rid of, let's work out A2. So if we want A2, if we apply minus 1 over tau, you can see here that minus 1 over tau for S here is going to give us a minus 1, and then 1 plus minus 1 is 0. So this whole term vanishes, leaving us with A2 s squared, which is is 1 over tau squared plus omega squared, and ka omega. So ka omega 1 over tau squared plus omega squared, and multiplying numerator and denominator by tau squared gives us this. So that's what we have for A2. Now for A1, to get at A1, we want to make this term vanish, and then the value of s which does that, you can see, is going to be I omega. So I omega squared is going to be minus omega squared, so minus omega squared plus omega squared is 0, so that will vanish. So if we apply s equals I omega, it makes that term vanish, and in this case it makes this term become 1 minus I tau omega and 1 plus I tau omega. And if you multiply those out, you can see it's going to be 1 minus I squared tau squared omega squared, and then the I squareds become a minus 1, and then that's a minus minus, and it's a plus. So 1 plus tau squared omega squared, and then you've got the ka omega here. So that's A2. And so that's why we chose A1 here, right? There didn't seem to be a reason for us to multiply by this 1 minus tau s here. That wasn't anywhere in the original expression. But we do it this way because we want two things to happen. We want this to get zeroed out, and we want this to stay real. So that's how we do that. So anyway, you apply A1 and A2 in there, and you can say that your original expression can now be expressed in this way, and here we just expand out for this term. So we break this down into a 1 and into a minus tau s. And so with a little bit of algebra, you can show that you have basically these three terms, right? And it looks quite long and complicated, but notice here, this is not an s function, right? This is simply a coefficient of 1 over 1 plus tau s. So this is just the exponential of minus t over tau. Similarly here, there's no s term. It's just s over s squared plus omega squared. So this is cos of omega t. And here also no s involved. It's just a coefficient. So this is sine of omega t. So that's all written here. And then if you are quite good at your trigonometric, what do they call those, not expressions, your identities, right? If you're good at your trigonometry, you can show that this stuff can be written as simply a shifted sine function. So your solution looks like this, right? And it looks complicated until you realize that, well, this is just a lump of constants. And so this is a constant times e to the minus t over tau. So this is simply the first order response. And anyway, this whole term is going to vanish as t goes to infinity. And then here, again, we've got a big lump of constants multiplied with a sine wave. And so this is a sine wave with a frequency of omega and an offset of phi, where phi is minus the arctan of omega tau. And I think here this is supposed to be a t, right? This must be a mistake. So this must be a t and that's a t, right? So anyway, that's what we have. And then if we apply that as t goes to infinity, this goes to 0, then we can say eventually what's going to happen is we are going to get a sine wave coming out, and it will have the same frequency as what we applied, because remember, on the input side we used a sine wave of frequency omega. So we again see an omega frequency, just that it's going to be shifted a little bit, right, by this amount phi. And we do know phi is simply minus arctan omega tau. So we are getting a sine wave out as well. And it didn't have to be this way. It's not automatically the case that if we stick a sine wave on the input side, then we'll get a sine wave on the output side. Similarly, it's not automatic that if you apply a ramp increase proportional to time, that you'll eventually get an increase in time in the same way. But it's a feature of this first order system, right? Because it's a first order system, this kind of thing happens, that we end up with the same types of time constants and so on. So anyway, for the first order process, if we apply a step increase, we get we don't get a step increase on the output, but we get something that does go up to a new value and a new level. If we apply a sine instead, then we get a sine wave out as well. If we apply a ramp increase, then we eventually get something that does look like a ramp. So the first order does give roughly similar features to the input space. Okay, and it gives it to us in specific ways, right? There are specific multipliers that occur in the solution that we see. And there are specific shifts, right? So that's referring to sine, but for the ramp also, there's a specific time that it takes before the function will start to look like the input. There's a specific new gradient that we'll get in the case of the process. Okay, so that's our first order process. Nicely behaved. And there is there's a nice example here. You've got a perfectly mixed gas phase reactor in which we have a first order reaction. We are trying to control the concentration in the reactor by controlling the feed rate to that reactor. So the inlet flow rate is controlled. The exit flow rate is a fixed constant. We want to find the transfer function for that, and we want to know about the responses to the step, ramp, and sine wave inputs. So we are given some constants here. So we've got the concentration in the feed, we've got the kinetic rate constant, we've got the fixed exit flow rate. Not sure why this is given, but anyway, I guess at steady state, that's the initial inlet flow, and so on. Okay, so I'm just going to skim through this. Please work through this in more detail through the solution. But anyway, your material balance looks like this. So assuming that the volume is constant, So for example, it's a gas phase reactor, or it's an overflow liquid phase reactor. So the volume is staying constant, so we don't have to worry about when we differentiate that we have a dV dt, right? So it's V is just a constant here. So V dc dt is the inlet flow, and that's the exit flow, so perfectly mixed. So the concentration in the reactor is the same as the concentration in the exit stream, is the same as the concentration that applies for the reaction. So the reaction term, this is a volume-based reaction rate, so we multiply by the volume here. And then at steady state, we can define the steady state versions of the input and the state variable. And so we can find those relationships, and we can rewrite this whole equation in terms of deviation variables. And we can then we can Laplace transform this whole thing, noting that we can replace this derivative by s uppercase C, and so we get our transfer function. And in this case, it looks a little different to what we're used to seeing until we recognize that this is a lump of constants here, and then you've got s here, and then this is all constant, and then plus 1. So this is nothing but constant over constant s plus 1. So it has the same form as what we are used to seeing here. And by the way, this was also multiplied by q in, which we recognize as our input transfer function. So that's our u of s. Okay, so that's our transfer function, and so we are ready to do all those nice things. We can apply the step increase, or the ramp increase, or the sine wave changes, right? And the solutions are actually shown here as well. Sorry about that. So if you apply a step increase, we've already shown that you get that kind of solution. And if we put that in the context of this question, our step increase we had defined as a delta q in. So q in was stepped up by delta q in. And then the constant we just showed here, the constant in front is simply this one, this stuff up here. So that's there. And then the time constant we showed was that 1 over q plus k. So this is the deviation version of lowercase c, and then the non-deviation version is going to be the steady state value plus the rest of it. So this is our actual time response. So this is the response that we observe in the output variable due to a step input, right? Then instead, if we apply a ramp input, then we know that we are going to get this kind of response. And so if we put that in the context of our question, substituting for our increase, right, the ramp gradient, that is. So if we apply the ramp gradient and we substitute for the k and for the time constant, then for our problem now, this is the response we get, and this is still in terms of a deviation variable, which we then offset by the steady state value, and then that's the response that we get. And then similarly, we can apply the sine wave input, and then we can take the sine wave solution and do the same things, and we can get the response for the system. So you see, we can take the general solution. If we just take our problem and recognize, yes, it's a first order problem, if we can identify specific lumps of constants, it's the same first order problem, then we can consider all these different types of manipulated variable time functions, and then we get the exact response. So that's the response of our first order process. Okay, moving on, let's consider now the second order process. So in second order, we have this general form, And let's have a look here again. So here's the form we are considering now. And you can see here it's still exponential functions, and it's just in a different arrangement, and you've got two different time constants. So you've got the sum of exponential functions with a different time coefficient, and there's a coefficient in front of all that. So that's our second order process, and we'll see just now how that comes about. Well, in fact, we'll see it now. So let's say we have this second order equation. So for example, let's say we have reaction diffusion. So we know diffusion is going to contribute a second order term. We might have convection, so convection will contribute a first order term. You might have the reaction itself here, and you might be applying some kind of control action. So you might be feeding to replenish the loss of some concentration, something like that. So for whatever reason, whatever your context is, you will have an equation in this form. And of course, if we turn this into a deviation variable, then we don't have to worry about the initial value. The initial value is 0. And so we can say the second order term here becomes an s squared capital Y. So we can see that here. The first order term will be an sy, so we get a sy. And then the undifferentiated term becomes a y itself. And I see here I'm missing my b for some reason. So there's a b here. And I'm missing that b down there. Okay, so this is the Laplace domain expression for the same equation up here. You can see there's a y in each of these terms, and so we can group each of these together, and we'll have s squared plus as plus b times y, and that's equal to cu. So we can write y divided by cu is equal to c divided by that stuff, right? So c divided by that there. So just check the steps there. So that's our transfer function now. And fine, it's a quadratic, and we can think about finding roots and so on here. So we know we can find the roots of this quadratic. So we can rewrite this in terms of those roots. We can rewrite it as s minus the first root times s minus the second root, right? So using nothing but quadratic solving, we can propose an alternate form like this. And so we can, well, in fact, yeah, we can then also recognize that if we divide top and bottom by R1, then this is going to be C over R1. And we can divide the R1 by this term specifically. And in fact, I see it's divided by minus R1. So minus R1, right, S divided by minus R1 here. And then you divide out that, leaving you with a 1 here. And then you divide again by minus R2. So minus R1 and minus R2, this becomes plus 1 over R1, R2 here. And then down here, this is minus 1 over R2S, and then plus 1. So it looks like that. And then we recognize this now has the same form as this equation here. If tau 1 is equal to minus 1 over R1, and tau 2 is minus 1 over R2, right? So you can see if you take a general second order equation, you can translate it into the same form that we expect here, and we can identify time constants, and then for this we have this nice second order solution. Where are you? Here. Right, so if you take your original system, right, let's say we'd gone and done our modeling, and we've found our coefficients A, B, C, right? We then just go ahead and solve that quadratic for R1 and R2, and then we take R1 and R2 and say, well, then tau 1 is minus 1 over R1 and tau 2 is minus 1 over R2. And then we just stick that in this expression. And then that will be the solution to that equation. Right, so that's how you can take your original differential equation and you can solve it in that way. All this time we've been ignoring this. We've been talking as if this is a zero. Of course, it's not a zero. We are going to apply different functions here, but for now we're just talking about how to take advantage of the second orderness, if you like, of the system. So anyway, that's how you can translate your function g. And now let's consider, well, I haven't gone on as yet to consider different inputs. That's what I thought I was going to do, but here I'm talking to my previous self here when I wrote these notes. But so if that was our original formulation, then if we want to solve this equation as a set of two first-order equations, we can propose y1 equals y and y2 is dy dt. And of course, y is y1, so this is the same as dy1 dt. It's a bit of a silly just relabeling there, but anyway, we can now, if we look at this, this is d2y dy squared. We are trying to get rid of the second order derivative here, and now if you look at y2, that's the same as dy dt. So the first derivative of y2 is the second derivative of y. So your second derivative of y you can replace by the first derivative of y2, right? You can see it here. dy2 dt is going to be ddt of this, which is d2y dt squared, right? So that's there. And then this term, a dy dx, should be t, right, not x. So dy dt we have already defined as y2. So we can replace this by ay2, right, which is what we do here, ay2. And then by, we in our new terminology is by1. And then we just leave cu as it is. So that is now the new form. It's as a first order equation, and we did that by introducing a new variable. So we do have this unknown function y1 here, but what we do is we just go ahead and regard this as another equation, and we say, well, to solve this, what we need to do is solve two first order equations now. So the first one is y2 is defined as dy1 dt, and then the second one we got from our model itself. So now we have the two equations needed to solve this system. Okay, so that's how we can solve a second order equation. So if you're worried about how am I going to integrate this equation, you just convert it to two first order ODEs, and we should by now know a lot about solving first order ODEs. Here I introduced all this to say, well, you can always convert a second order ODE into two first order ODEs. And so I think the reason I was saying this is because don't think second order equations are uncommon. It might be that your original model looked like this, right? You had two things. Imagine you had two concentrations in the reactor, and the first concentration was changing according to this rule, and the second one was changing according to this rule. And so implicitly behind these two equations, there is a second order relationship that exists, right? If we could get to these two equations from this equation, then that means implicit to their behavior is a second order behavior here. So two equations might actually be a second order form, and we can then say the same second order style of things would apply in that case. Now, I also want to say here that it's not always the case that two first order equations necessarily mean you have a second order process. And I'm giving here an example of that. So in this case, we have no relationship between these two variables, right? You see if K1 and K2 and K3 and K4 are all constants, here this equation has no need, you can solve this equation independently of solving this equation. And this one also, this can be solved without solving this, right? If you needed a y1 in here, then you could solve this by itself, but then you would need to use that solution in here. But this one also doesn't use a y1. So these two equations are totally independent, and so it's not second order. These two first order equations are not inherently second order. So these are two first order relationships. So even though I'm just saying this now to be strict and to say it's not necessarily that whenever you have two first order equations that means it's second order. No, it is possible that it's not. So you have to look at your system, understand what it's doing, look for whether or not it's second order. So don't look for automatic easy rules that don't apply. Here's another example. If you have first order elementary reversible reaction, so you've got component A being converted to component B, and then B can go and react back to give us component A again. And if these are both first order, then this simple model applies. So the rate of change of A is lost in the forward reaction, and it's regained in the reverse reaction. And in the same way, B is formed in the first reaction and it's lost in the second reaction. And the way that you can figure out, you can see these two are related, right? You can see a B here. So clearly you need the solution to the second equation to solve the first equation. And the same down here, you need the solution to the first equation to solve the second equation. So we don't want to work with this. Can we find the second order equivalent to this? And you can do that simply by differentiating. And by the way, that doesn't mean that if you want to make it look like second order, you just go and differentiate it one more time and hey, you've got a second order. No, that doesn't work, because that's a kind of false. You can try and kid yourself that would be second order, but you would always be able to integrate that equation one time to say yes, actually it's first order. So we are not differentiating just to make it look like second order. We are differentiating now because we then get dCB dt here, and we can realize that dCB dt is actually minus dCA dt, right? If you look at these two equations, if you multiply this by a minus 1, you get K1CA, and there's K1CA, and then you get minus K2CB, and that's minus K2CB. So clearly dCB dt is minus dCA dt. And so if we differentiate this equation, let's say we take this equation and differentiate it once, then we get d2CA dt squared minus K1 dCA dt plus K2 dCB dt. And then we can get rid of this dCB dt here with a minus dCA dt. And so that's there. And now we have this nice relationship. Right, so this is, and in fact you can integrate this once and say, well, this is first order. But in this case we can say we used a second order, we went into the second order domain for a little bit to find the relationship that we were looking for. So so that's another example. And then here's another case. If we have processes in series, so this case wasn't second order because actually there's a kind of circular relationship here. But here, if we have processes in series, so if you have two tanks in series where the flow from the one tank is the inlet to the second tank, then you can say the rate of change of mass in the first tank is the flow rate coming in minus the flow rate going out. And then the rate of change of mass in the second tank is the flow leaving the first tank minus the flow leaving the second tank. And then let's say we had these constants k1 and k2, then we can relate them in this way. So you can do the usual thing, write in terms of deviation variables and find operating just on the first tank for now, right? This is independent of the second tank. If you look at this, we don't need the second tank solution to solve this equation. So you can find the transfer function for the first tank, and you can invert it, and you can get the solution in the first tank. And then for the second tank, we have to use what we found in the first tank. So we Laplace transform for the second tank using the first tank's Laplace transform, and then you will find this constant times s plus 1, constant times s plus 1. And so you can rewrite this whole thing in this form, which is our second order form. Right? So for tanks in series, it's not possible to find a first order relationship. And that's if you are trying to work on the second tank. So if you are trying to control the level in the second tank, it is inherently inherently second order with respect to the inlet flow to the first tank. So read this thing in detail to understand all that stuff, right? But what I want to do right now is take a step back and look at numerically what all this looks like. So going over to our trusty Python formulation, let's increase that a bit. So here we are looking at simulating our dynamics, and let's just get something reasonable here first. Just going to rerun this. Right, and I'm going to scale back a bit on this. Anyway, let that tick along a bit, and let's look at the code. So here we are actually looking at this oscillating spring example. So the oscillating spring, the mechanical engineers like this type of example, right? For your oscillating spring, if you have no friction, then C is 0, and you have the second order related to the 0 order. So that's the true oscillating spring, and then you have damping here if you have friction in the system as well. And then typically you would force the spring to some non-zero, so the rest position is 0, x equals 0. And then if you force x0 to non-zero, then you have your oscillation happening. So let's see if we can make that. Let's switch off the friction, and you can read through the code here. I'll point out any unusual features, but it's the same differential equation that we looked at an example last time of creating differential equations. And so with no friction and an initial condition of 1, so we've moved it away from the 0. Let's see how that system responds. And by the way, I've got, yeah, okay, that's fine. So you've pulled the system away from 0, so that means it's going to keep oscillating, right? It's frictionless, so the system oscillates like this. And we are plotting here y1 and y2. y1 and y2 are actually the y1 is it's actually x1, and y2 is dx1 dt. So that's just the derivative that's being plotted there. And so you've got this oscillating effect. And now notice here that nowhere have I specified a sine wave, right? If you look at this system of equations, there's no obvious sine wave in this equation. And even when we translate it into two first-order equations, there's no sine wave here. There's nothing in the boundary conditions about a sine wave. There's nothing in the code about a sine wave, right? But a sine wave we have. And that's because a sine wave is inherent to this problem, right? If you translate this, right, if you translate the system of equations into time constants, right? If you find the time constants of this equation, and we'll look at later in detail how to do that. If you find the time constants here, you find that the associated values are imaginary, right? The solution has e to the I t, I omega t, and that is going to give us an oscillating function. So it's a feature of this differential equation that it is possible to get sine waves. So we will look at how that occurs exactly. But again, we got this under the condition of a damped oscillation. Let's undamp it. Let's put in a weak damping influence. And if we do that, you can see then that because of friction now, this is oscillating and it's coming in towards zero. So if we go for long enough, it's going to oscillate to zero. And in fact, let's just crank this up here, put in more friction. And you can see it damps out and it goes back to the zero. And by the way, this interesting plane over here, this is just taking the two values for y1 and y2 and plotting those one against the other. So here we are plotting y1 and y2 as functions of time. So instead of plotting as a function of time, if we took time slices, let's say we took at time 0, then that's the value for y1 and that's the value for y2. So we could find that point. We could say at at that time 0, y1 has this value and y2 has that value, so that's a point. Then shift the time a little bit, then you've got a new value for y1 and y2 that gives us a new point, and so you generate all these points. And so as we are looking, as time moves left to right here, time is actually moving along this curve here, and you can see our solution is spiraling in here to 0, 0. And here you can see as time marches on, we are going in towards 0, 0. So this is the so-called phase plane. It's showing us how our state variables are changing simultaneously, and that's giving us a different view of the same solution. So all three curves shown here are the result of the same simulation, right? And we can play around with the time constants of this system. So by shifting A down, I am increasing the, well, let's look at it. A is K over M. So K you can think of as the stiffness of the spring, right? K here, right? That's the stiffness of the spring. So by shifting A down, I'm increasing K. And so the spring is getting stiffer, so it's giving us a faster response here. And B relates to C, so the higher the value of B, the smaller the damping. So if I increase that, then it decreases the damping, so the oscillations live for longer as I do that. And now look at this, as B increases further, you are getting divergence, right? So your damping it's like the opposite of friction. In this case, your system is causing your oscillations to increase, right? Physically, it's hard to imagine that happening, but anyway, mathematically, we can simulate that happening, that now we have an environment which causes oscillations to increase. And so just by increasing B beyond its critical value, you can see now the spring is diverging. It's whacking around even more and more. So in this case, your phase plane is actually spiraling outwards, right? So the point of looking at this is that the dynamics of the system, right, how the system is responding in time, that is strongly dependent on the constants here, right? It does depend on these coefficients. It's not as if the solutions we get are just being scaled a little bit by these constants, right? The nature of the response is changing as those constants change. And in our context of trying to control a process, this is especially relevant. So when we implement a controller, that tends to change the characteristics of the system. And so that's shifting constants around. And you can see you can change behavior, and you can get things that look that don't look safe, right? In this case, where our oscillations are growing, that doesn't look like a safe situation. And so if we choose the wrong controller settings, we might end up in a situation like that. So up to now, we've been talking quite abstractly and mathematically about Laplace transfer functions and so on. And we are going to exploit what we can find in the Laplace domain to manage our controller settings so that we avoid risky situations like this, and also so that we get some good control at some stage. So that's what we can see in the context of our differential equations. So for a second order process, we can see there are many ways that we can find second order behavior in our system. And going back to the notes, we can start trying to categorize all the behavior that can arise. So here we were looking at ways that we could find second orderness in our processes. Now let's look at what happens as we try different inputs to our second order process. So once more, we've got our second order process, and now we want to apply a step response. The first thing we'll do before we actually apply that is to just multiply out this denominator. So we can see this is a quadratic, so s squared, and then of course you'll have tau 1, tau 2. So tau 1, tau 2 is going to be the coefficient to s squared, and then we'll get a tau 1s plus a tau 2s. So it's tau 1 plus tau 2 times s for the second term, and then 1 for the third term. And we are going to propose that we can create this form. So instead of a tau 1 tau 1 times tau 2 for the s squared, we are going to say, well, let's just say there's some number tau, and tau is such that tau squared equals the coefficient that we want here. And so obviously then you can say tau squared is equal to tau 1, tau 2, right? Then we are also going to introduce a number zeta. So that's the Greek symbol zeta. And we just said the coefficient of s is going to be tau 1 plus tau 2. So we can say 2 zeta tau equals tau 1 plus tau 2. And then we don't do anything to the third term. So it's a simple translation, right? We are just looking for numbers tau and zeta instead of tau 1 and tau 2. And we'll see just now that there's a reason for this. It makes things a little more convenient, right? That's all we are trying to do, make things a bit more convenient. There's no real meaning behind this. Or well, you can interpret these numbers, but there's no deep meaning here. We are just saying, well, let's rewrite this product in this quadratic form, right? So now we've just represented our transfer function slightly differently. And now we are looking at a step response. So the response to an applied step, which we saw earlier, was that. And so our overall, this should be the response, right? So this should be ys, not gs. So the response is this in the Laplace domain. And if we plot out the solution to this, right? Remember, we talked about the time version of this. So we can plot out the time version when we apply the step response here. And we will look at that in a bit more detail in the next lecture. But anyway, for now, we can say if you go and plot out for the second order process with time constants tau 1 and tau 2, you will get this kind of behavior. And you can see an oscillation in here. And this is the step input response. This is not a sine wave. We didn't put a sine wave in here. We put in just a step increase, and we got out this response. So you get an oscillation in the second order case. In the first order case, we didn't get that. In the first order case, we got this exponential saturation, and it settled down peacefully to the new value. In this case, it's going to bounce past the value. It's going to bounce back and then eventually settle down to that value there. So it's going to overshoot the intended final steady value. And this is important to us, right? How far it bounces past the steady value and how far it dips below it, those might be critical numbers, right? There might be some safety issue in bouncing too far past the steady value here and in going too far below here. So we have to be aware of this in developing our control. And so we can at least enumerate all these possibilities with this zeta number. So because we have this nice representation in zeta, as we change zeta, we can see how far this thing is going to bounce above the value. Here we are looking at zeta in a different range. So these are this kind of behavior can be observed in the so-called underdamped response. So when we were looking a little earlier at this oscillating spring example, we saw we got oscillations if we applied a stiff enough spring. If the spring is not stiff enough, or if the friction is high enough, then we actually don't get this kind of bouncing effect. So if the system is damped and overdamped, then we won't see oscillations. The system will just behave like this. But the moment we start going into this this range of values for zeta, so if zeta is 1 and above, you just get this peaceful transition to the new steady state. But the moment you go below 1, you start seeing oscillations appearing. And you can say, well, then isn't it clear? Let's just use 1 for zeta every time, and we design our controllers so that we don't get this bouncing around. So you can do that. However, one thing you'll notice here is that it's taking a fairly long time to settle down to the new steady value. Whereas here, we can see pretty quickly we got to the new value, and fine, we overshot it, but we got in the right range much faster. So we want to think about that. In our control, we don't want such a slow response always. It might be that there's better control. If we can control how far this bounces around, then we could get to our intended operating region sooner. And that might mean major economic benefits to us if we can control our system and get into the new region faster. So knowing our system dynamics, right? Knowing tau 1 and tau 2, knowing the influence of zeta on that system, you can see is going to be quite important in designing this controller well. So zeta emerges as a nice damping coefficient. So we said it was a convenience. It's a little more than that. We can interpret zeta as a damping coefficient, as it turns out. Skipping over the ramp input, we don't really have ramps in control, right? We don't go and apply a ramp and let the thing go on forever with time. We normally want to control how far. So step inputs to some controlled level and sine wave inputs. Those are all more reasonable things you can do with your input. So here, if instead of a step input, and yeah, all this was for a step input, right? There was no sine wave, but we got oscillations. Anyway, I think we said that. So carrying on, looking at a sine wave input now. Our U we saw before, if that's a sine wave with amplitude uppercase A, then the sine part is going to be omega over s squared plus omega squared. And then our transfer function G is simply that. And then we had found before, we found a way to separate this out, well, for first order case. Anyway, I'm not showing the whole transformation in this case. But we apply again these variables. So tau is the square root of tau 1, tau 2, and zeta is this lump. And our phi, again, that arctan function, so that's all the same. And now we can show that we get this response. So the response of a second order process is also a sine wave. However, the amplitude is showing some misbehavior here. We can see that the amplitude of the response is a function, and it's a fairly strong function, of the frequency itself and this lumped time constant. The sine wave is shifted by phi, and well, it has, at least we can say it has the same frequency as the applied sine wave. So we can go ahead and graph the output, which I don't seem to have done here. But anyway, what we can say here is that there does exist this amplitude issue, right? And they define an amplitude ratio. So in the field of control, we can define the amplitude ratio as the ratio of the expected amplitude increase. So we know that there's an applied amplitude, so we expect the output will be scaled in some way according to that, and we know the output constant is k, so we expect that kind of scaling for the output. We didn't perhaps really expect this part as well. So we can define the amplitude ratio as the ratio of the obtained amplitude divided by the expected amplitude, which is Ka. So this is this unexpected part, right? So that's what we can get in terms of our amplitude increase for the second order process if we apply a sine wave. And what we can do now is, well, we can identify that at certain frequencies, there exists a frequency at which this this oscillation is going to be quite severe, or there exists a frequency where we get the maximum unexpected increase. And perhaps let's look at this here. So fine, this is not the second order sine wave response. This is the second order step response. But you can see there's a maximum amplitude increase here, and then the amplitudes after this are lower, or not amplitude, the low point and the high point. Those are not as far away from the steady state point as this first one. So we want to know what's the frequency at which this happens. What's the omega value where that happens? And we, because we've got this amplitude ratio, we could differentiate this with respect to omega and take the gradient where that derivative is 0, and we can solve for that omega value. And in fact, here's a nice plot of that, right? If you take this function and you graph it as a function of tau omega, you find that you get a maximum here. It's graphed nicely against these zeta values less than 1, right? So at 0.1, you can see you've got quite a sharp amplitude increase. So if you go and differentiate your amplitude ratio by omega and set that to 0, then you can find the frequency which gives you the maximum amplitude ratio, which turns out to be, well, it's this value, right? So you've got the frequency, and then you can go and stick that back in here, and that can tell you then how high your signal is going to go. So if you knew there was a safety constraint, you could then design it. You can say, well, I cannot tolerate an amplitude beyond this value, so I can solve backward and say, I need to stop the system from ever having a frequency in this range, right? So that's the application of that. Okay, so that's the kind of stuff we are looking out for. So in this lecture, we are still staying at a slightly high level. We aren't getting into the detail of exactly how to do all this. We are just trying to point out there are certain features that we can look out for. We're starting to see the implication of control emerging here, and we are going to look in the following lectures at exactly implementing control. Just looking a little further, there are a few more tutorial questions that are all worked out for you here. And you might say, well, all this looks quite useful, but it's all for these nicely behaved first order and second order processes. What if we have a nonlinear system and we want to use this kind of logic? And you can use this logic because you can you can find linearized forms or linear approximations. So if you have some nonlinear differential equation, then using that deviation style concept, you can expand, and it's more like a first order Taylor series expansion. You can expand this nonlinear function into a steady the value at some steady point, plus the derivative with respect to the output multiplied with the deviation from the steady state, plus the derivative with respect to the input multiplied by the deviation of that input. So if you regard that derivative as approximately constant in the region of the steady state value, then it's a constant multiplied by a first order term here. So this is a linearized version of your nonlinear equation. And then all the arguments that we are advancing now apply still. Okay, so that's it. We are looking at the response of our first and second order processes to our inputs. And it should occur to you, well, what kind of control is this where we are just putting in step increases and applying sine waves and so on? We will look at error-based control as an extension of this. For now, we are just looking at the response of our first and second order processes. So what we learn in